Welcome to today's Explainer. So, if you're building apps with AI, or honestly if you're just curious about how these massive large language models actually work behind the scenes, you've probably heard the word token thrown around a lot. But let's be real, it's a concept a lot of us just kind of take for granted, right? We treat it like this magical black box that somehow swallows our text and spits out an answer. Well, today we're prying that box wide open. We're going to decode exactly what happens the second you hit send on a prompt, and we'll uncover the hidden math powering the AI tools you're using every single day.
Here's our roadmap for cracking this token mystery. We're going to start with the token knowledge gap, then check out the Hello World mystery. After that, we'll dive into encoding and decoding explained, move on to building a token vocabulary, and finally, we'll wrap things up with the cost of unusual words.
All right, part 1, the token knowledge gap and the AI workshop disconnect. To really set the scene here and show you why this foundational concept is so critical, I want to take you to a recent AI workshop over in Poland.
The instructor at this workshop asked the developers in the room a super straightforward question. He just said, put up your hand if you know what a token is. And the result? Actually pretty shocking. Only about a third of the people in the room raised their hands. Think about that. Almost everyone there is prompting these models daily, wiring them into apps, paying the server bills, but very few actually know what's going on under the hood. There's this massive disconnect between how often we use the tech and how well we actually understand its foundational building block.
So let's just define it right now so we're all on the exact same page. A token is the absolute fundamental currency of large language models. It's the unit used to measure and bill both your input text and your generated output. When you send a prompt, you're charged this tiny, infinitesimally small amount per 1,000 tokens. And it's a two-way street, right? Your total API cost is calculated by taking the build input tokens you send to the model and adding the build output tokens the model generates back for you. And here's the kicker. Those output tokens require way more compute power to generate, which is exactly why they're usually billed at a much higher rate than your inputs.
Which brings us to part 2, the Hello World mystery, a tale of two models. Let's see how that definition builds into a pretty fascinating discrepancy when we actually put it to the test. Just look at the sheer difference in input tokens here for the exact same two words. If we send a basic Hello World prompt to Anthropic's Claude 3.5 Haiku, the API usage tells us that took 11 input tokens. But if we send that exact same Hello World text to Google's Gemini 2.0 Flash, it only uses 4 input tokens. Same letters, same exact meaning, completely different token count. No way, right?
So why on earth does the exact same text sent to two different models result in a totally different number of tokens? I mean, if a token is just a standard piece of text, that shouldn't happen. So what exactly is the hidden relationship between the text we're typing on our keyboards and the tokens the model actually sees? To solve this, let's jump into part 3, encoding and decoding explained, or how LLMs actually think. Because, spoiler alert, these models do not read the way you and I do.
Let's walk through the full end-to-end pipeline to see what's really happening. When you pass in your raw input text, the system first splits it into the largest chunks it knows about, based on its specific vocabulary. Next, it encodes those text chunks. That just means it assigns a specific ID number to each one. Then, the LLM actually does all of its complex thinking using only those numbers. Finally, the model outputs more numbers, which are then decoded back into the human-readable text you actually see on your screen. So all that heavy computational lifting, it's happening on numeric representations, never the text itself.
So the crucial realization here is that LLMs literally do not read text. They read arrays of numbers. The model is quite literally doing math on language. For example, OpenAI uses a tokenizer called TickToken, specifically one known as O200K_base for models like GPT-4o. When that tokenizer sees your text, it cross-references words or subwords in its specific dictionary, its vocabulary, and converts them strictly into ID numbers.
Let's test this out to see how much text a token really holds. If we take a 2,300-character story about, say, a wise owl of the moonlight forest and run it through the GPT-4o tokenizer, it compresses all the way down to less than 500 tokens. It basically returns an array of less than 500 numbers. This proves that tokens are much larger chunks than just single letters. The tokenizer is grabbing whole words or big chunks of words at a time and compressing our human language into a highly efficient numerical format. And that leads us straight into part 4, building a token vocabulary. Now that we know what tokens actually are, to understand why they differ between providers, we really have to look at how these vocabularies are built in the first place. Imagine you're training a model's vocabulary from scratch. Now, if you built a simple character-level tokenizer, every single letter would be a token. A word with 11 characters equals 11 tokens. Simple, right? But actually, that is incredibly inefficient because it maximizes the workload for the LLM. It would have to mathematically predict every single letter. So instead, we use a Subword-Level Tokenizer. This kind of tokenizer scans massive datasets and groups commonly occurring letters together. For instance, the letters T and H pop up together in English all the time, so it just makes sense to group them into a single token. Doing this drastically cuts down the total number of tokens the LLM has to process, which saves massive amounts of compute power.
Let's look at how the physical size of a model's vocabulary literally changes everything. Say a model has a tiny vocabulary of just 1,000 tokens. It might have to awkwardly chop the word understanding into 5 different tokens: under, sta, and ange. Now, if the vocabulary grows to 50,000, it might recognize larger subwords, chopping it into just 3 tokens. But if a model has a massive 200,000 token vocabulary, it likely recognizes the entire word, processing understanding as just 2 tokens. Bottom line, the bigger the dictionary, the more efficient the chunking.
Now you might be wondering, well, why not just make the vocabulary infinitely large? Well, it all comes down to hardware constraints. Larger vocabularies absolutely mean fewer tokens for the LLM to process, making the actual generation faster. But a larger vocabulary requires a physically larger model to house it, and that larger model takes up significantly more RAM to execute, which means much higher hosting costs for the companies running them. This trade-off is the exact reason for our Claude versus Gemini mystery from earlier. Anthropic and Google simply made different engineering choices regarding their vocabulary sizes and memory limits, and that resulted in a completely different number of tokens for the exact same Hello World text.
Okay, moving on to our final section, Part 5, the cost of unusual words, or as I like to call it, the frumious problem. Let's dive in and see how this subword math practically impacts your wallet and your app's performance when you're dealing with unusual language.
Let's take the word frumious from that famous Lewis Carroll poem, The Jabberwocky. Carroll totally made this word up. And because it's a made-up, unusual word, it didn't appear frequently in the massive datasets the tokenizer was trained on. So when the tokenizer encounters frumious, it doesn't have a single neat ID number ready for it. Instead, it has to awkwardly chop this rare word into 4 separate, expensive fragments. Basically, writing weird poetry for an LLM will literally cost you more money. Unusual words almost always equal more tokens.
And this exact same logic applies beautifully to developer practices today. If you're prompting an LLM with code, a super common language like JavaScript is going to be incredibly token efficient. Why? Because there are massive amounts of JavaScript repos on GitHub that were included in the training data, so the tokenizer recognizes those syntax chunks instantly. But if you prompt with 20 lines of a rare language like Haskell, the tokenizer just isn't used to those specific character combinations, so it breaks the code up into far more tokens. There is a huge hidden advantage and real cost savings in prompting with widely used languages.
So, there we have it, the underlying math of how LLMs actually read. Tokens are the numeric chunks LLMs actually think in, and they're shaped entirely by the size and the training of the vocabulary the model was built on. Now that you understand the hidden math and structure of tokens, how is this going to change the way you write your prompts and build your future AI applications? Are you going to stick to common phrasing to save on costs, or maybe rethink which model you use based on their specific token efficiency? Definitely something to think about. Thanks for joining me on this explainer, and keep learning.